Hi guys, today we're on Unit 10, Lesson 1, and we're doing an introduction to limits. The idea of a limit of a function is what connects algebra and geometry to the mathematics of calculus. This topic is very, very important in the study of calculus itself. Some basic notes. The limit of a function is the y value for which the function is approaching as x approaches some c. So what that means to us and our notation when we're evaluating a limit problem, it will look like this. The limit as x approaches c of some function f of x is equal to some number L. Remember, we want to remember this is just a y value. Okay, it's just going to be a number. And I usually include, when I discuss and introduce this unit, just like a little graphical representation. So that's going to be my function. That can be anything. This is just our general function. What this definition means is, as I plug in numbers that get close to some number c on the x-axis, our y values are getting close to some number L, right? So our y values are approaching some number L, which is really just a number. Some different ways we're going to evaluate limits in this class. Numerically, which means we're going to use our values from a table in our graphing calculator. Graphically, we're going to work right from a picture of a function and a direct substitution. And that means just plugging in x. This is not going to mean that much to you right now, but it will over the next couple of days. And I will mention to you at this point in time, these are the two methods that we're primarily going to focus on. I just use the table to help us understand the concept of what a limit really is. So we're not going to be, after today's lesson, you're not going to necessarily be setting up a table like we are right now. Okay, so don't think that it's going to be this complicated over the entire unit. So when we want to set up a table of values numerically, or when we want to look at something in our graphing calculator, I'm going to mention something right now. Okay, remember, we want to plug in numbers that get close to 3. Okay, this what we're doing here is we're evaluating the limit as x approaches 3 of our function f of x squared. So if you think about numbers that get really, really close to 3, okay, you could think like on the x-axis here, if you think about it like this. Okay, a number a little bit bigger than 3 is 3.1, but I could even get closer. I could do like 3.01 or 3.001. Okay, so just to make our life easy, we're going to kind of go into our calculator for a moment and adjust our table. Now we're going to go into a second table set, and we're going to have our delta x be 0.001. And what's that's going to do to for us is our x values are going to sort of look like this then, if this makes any sense whatsoever. Okay, so see how my numbers are getting close to 3, and on the other direction, 3.003, 3.002, 3.001. Now you could do this differently, but if we all use the same delta x, so to speak, change in x, everyone's answers are going to be the same. So first thing I'm going to do, I will plug in my equation, 5x squared. The next thing I'm doing is I'm going to adjust my table. So I'm just going to go to 0 right now, and adjust it later. And notice you might have your table going up by 1 unit. What you're going to do is that table, you're going to clear that out. And what this is going to do, it's going to change your X inputs, and they're going to go up in decimals. I'm going to look at the graph of this function. It is a parabola, so the table doesn't do anything but give us Y values. Now, if I notice on my table now, if I look at my X values, I want to be, the number I'm looking for here, I want to have my numbers close to 3. So when I usually begin a problem, I go right up to the top and I put the number in that I'm getting close to. And now we can take our Y values, right? Those are our function values. So when X is 2.997, Y is 44.91. When X is 2.998, Y is 44.94. When X is 2.999, Y is 44.97. I'm going to jump over 3 for a minute, because technically a limit, the definition is you don't care what you get when you plug in 3. You care what you get when you plug in numbers close to 3. So if I go on the other side, when I plug in 3.003, I get 45.09. When I plug in 3.002, 45.06, and 45.03. So let's go back to this concept. As my X values get closer to 3 from either direction, what's happening to your Y values? They're getting closer to what number? 45. So the limit as X approaches 3 of 5X squared is 45. Now in this case, when we plug in 3, we actually get 45. Okay. So our limit matches our function value, but that's not always going to be the case. So just, like that's why we're doing the table right now. If I look at my next graph, so now this one I'm evaluating the limit as X approaches X plus 1. That's my function. You could probably do this one in your head. Maybe we should. And my table as X approaches 1. Obviously, that's a line. If I go for my table of values, oops, 0.997, 0.998, 0.999, we're going to go and fill in our table. One 1.003, 1.002. And our Y values, when I plug in, I get 1.997, 1.998, and remember, I'm leaving this one blank on purpose. As I plug in numbers that get close to 1, what's happening to your Y values from either side? They're getting close to what number? 2. Again, it matches what I get when I plug in 2, but we're not going to get too concerned right now. For our next example, example 3, I have the limit as X approaches 1 of X squared minus 1 over X minus 1. Go back up to Y equals X squared minus 1 over X minus 1. This is a rational function. It looks like a line. We could talk about that in a few days, why that looks like that. Today, we're just practicing evaluating limits. Again, we're going to set our table. We're focusing on 1. So our x values that we're plugging in, 0.997, 0.998, 0.999. When I plug in 0.997, some of you may already know what's going on, and that's great. If you don't, just read your table. 1.003. When I plug in 1.003, I get 2.003. So as my x values, right, as I plug in x values that get closer to 1, my y values are getting closer to 2. But this time, what happens when I plug in 1? I don't get an answer. I still get a limit though, right? In the graph of the function, as I plug in x values, I still get my function. I may not get an answer when I plug in 1, but my y values are getting closer to 2. And the limit is what's happening to the y values as x gets close to some number. Oh, I'm going to slide this. Let's try one more example here. This time I'm getting close to 2, so I want to jump my calculator to 2. My x value is 1.997, 1.998, 1.999. Notice my x values are getting closer to 2. My y values, oh, my eyesight is so bad, negative 1,332, negative 1,999, negative 3,999. When I'm bigger than 2, my x values, when I plug in 2.003, I get positive 1,334, 2001, 4001. So as I plug in x values that get close to 2, what's happening to my y values? They're going down to negative infinity. When I plug in x values that get closer to 2, my y values are going up to positive infinity. If I want to kind of make sense of this, if I look at my picture, right, on the right side, when I'm bigger than 2, my y values are going up to infinity. My y values are going down to negative infinity. A limit has to be a number. Okay. If I go to infinity and negative infinity, like I am at this asymptote, we say the limit does not exist. When I plug in 2, I don't get an answer. And here my limit does not exist. And yes, we are going to be discussing this more. But for tonight, for this part of the lesson, I want you to just practice a couple of these limits using this method. Now let's look at not having a physical equation to plug into, just looking at a graph. So the graph of a function also can be helpful in finding limits. In each graph below, we just want to notice what's going on as x gets close to c. So in this first example, in example A, the limit as x gets close to c, our graph is getting close to some number n from either direction. In this next example, in example B, The limit as x approaches. So as I plug in numbers that get close to c, notice on your graph, your y values are getting close to n, but your function value is somewhere else. We still get a limit. This has a limit. This has a limit. In this case, f of c is not defined. As I plug in x values that get close to c, I may not have a function value, but once again, my y values are getting close to some number, so I still have a limit. So we want to kind of just break down this concept of plugging in numbers. If we talk about something called a right-handed limit, we're referring to numbers that are bigger than c. Our notation for this is going to be the limit as x approaches c from the right. That little plus sign means you're approaching c from the right. So for instance, I would only be focused on the right side of the function, the right side of c. Verbally, again, the limit as x approaches c from the right. If we're evaluating a left-hand limit, these are numbers that are smaller. And then you're only focusing on what's happening on the left side of the number in question. Again, verbally, the limit is x approaches c from the left. And when you compare these two numbers with no sign, like we did in the previous example, we're evaluating the limit as x approaches c. Okay. In this case, we need to consider both directions when we're analyzing the graph. Now, in this course, this is mainly the limit we're going to be evaluating, but we just want to be careful if we ever see one of those pluses or minuses. So now we're going to take a look at finding limits from the graph of a function. Okay. And we want to mention here, notation is very important. We want to learn to read the math. So we need to know the difference between f of 2, a function value, and let's say the limit as x approaches 2. Okay, so that's what we're going to talk about in this next little section here. Use the figure above to find the function values and evaluate each of the following limits. In question 1, I'm evaluating f of 2. So that means I'm going to go to 2 on my x-axis, and then I'll look for the closed-in circle. That's my function value. So f of 2 is -1. In example 2, f of -1, well, that's going to be 4. In example 3, I'm evaluating the limit as x approaches 4. That little minus sign means from the left side. I'm going to go to 4 on my x-axis. The left means I want to know what's happening to my y values as x's get closer. So as I plug in x, getting closer to 4, my y values are getting closer to 3. The limit as x approaches 2 from the right. Again, I'm going to go to my x-axis. As I plug in x values that get close to 2 from the right, my y values are getting closer to 1. I don't care that there's an open circle there. It just means if I plug in a number a teeny weeny bit bigger, just a tiny bit bigger, my y value is going to be close to 1. The limit as x approaches 2 from the left. So as I plug in x values that are less than 2, my y values are getting closer to -1. The limit as x approaches -1 from the right. I go to -1, go to the right, as I plug in x values that are getting closer to -1, my y values are getting closer to 2. The limit as x approaches -1 from the left. I should have done the left there. Sorry, I knew I was doing something wrong. It's not going to matter. It's still 2. So left and right are both 2. The limit as x approaches -4 from the right. -4, go a little bit bigger. My y values are 2. The limit as x approaches -4 from the left. If I go to the left side of -4, I don't have a graph. So the limit does not exist. Now let's be a little bit more specific with our notation here. The limit as x approaches -1. Okay. So when I'm looking to evaluate the limit as x approaches -1, I need to consider both directions. Does my left limit match my right limit? You could see it on the picture that it does. You could see it from the work we just did that it does. When both numbers are the same, the limit as x approaches -1 is going to be 2. In 11, the limit as x approaches 2. Again, we did the work up above, but we can also just from the graph, the limit as x approaches 2, I'm going to look from the left, I'm going to look from the right. Okay, and what I see here is just a break in this graph. There are 2 different numbers. That limit does not exist. The limit as x approaches 5. I go on the graph of the function. The limit as x approaches 5. If I look in both directions, okay, this graph basically is going down. So when I analyze this, there's no holes or breaks or anything. So I'm just going to take the y value. And I'm going to look from both directions. And since it's the same from either direction, it's going to be the y value of the function. The limit as x approaches 0. Again, this is a little easier to see. I go to 0 on the x-axis. I go to the graph of my function. My answer is -1. The limit as x approaches 1. It's the same from either direction. It's -2, right? Okay. Which one did we not do that I wanted to do? Oh no, we did everything. Okay. The last little one I just wanted to add in. Didn't really mention this. I'm going to throw it in here now. How is this different? Okay. And we are going to talk about this in more depth later on in the unit. But what's happening? What's the limit as x approaches infinity? Now, instead of looking at what's happening as I approach a number, I'm looking at what's happening to my graph as I plug in bigger and bigger numbers. What do you notice with this function? My y values are getting smaller and smaller. We could say that this limit does not exist because it's not a y value. However, when we're dealing with infinity, we can use -infinity to describe our answer. So we just want to be aware of little things like that. Okay. My goal for you today is just to sort of understand this component here. This we will work on as we move through the unit. Okay. So just kind of review. A limit existence theorem means if the limit as x approaches c from the left equals the limit as x approaches c from the right, then the limit as x approaches c equals some number L. Okay. That's a lot, and our big focus is going to be that guy. 3 cases where limits don't exist. Okay, we sort of already saw some of them. The limit as x approaches c will exist if and only if the 2 limits match. Okay. Cases that fail to exist. In the first example, the left limit does not equal the right limit. I'm not going to really worry about justifying right now. Okay. It's just this would be a limit does not exist. So when you see a jump in the graph, you could say the limit does not exist. In the next case, when you see something like this graph, how it's going up and down like that, that's an oscillating behavior. Is another example where the limit does not exist. Okay, and that means our graph is bouncing back and forth. It's not a smooth curve like a sine function. It's going up and down really quickly. That's going to be an example where a limit does not exist. And in the last, our limit is going to go, our limit goes to infinity. From either direction. In other words, we're going to have an asymptote. So when there's an asymptote, the limit does not exist. And we are going to kind of in a few days go into a little more depth. Okay. Right now, I just want you to visually be able to see the instances when the limit does not exist. Okay. So that was a lot for today. Okay. I want you to do a few homework questions tonight and just do the best you can. All righty. Thanks, guys. Have a good day.